Okay, thank you very much. So, good morning, good afternoon, or good evening, depending on where you're watching this conference from. Thank you for joining my session, Mysteriously Optimized Nested Loops. During the session, I will discuss some lesser-known optimization techniques that SQL Server utilizes when nested loops joins are used in an execution plans. The reason why I prepared this session is that I would like to share some findings while I've been troubleshooting a very strange behavior of quite simple select queries on our production server. So, before we start, just a few information about me. My name is Erik Dosa. I work as a SQL developer at GreenTube, Slovakia. I have years of experience as a data warehouse ETL developer using mostly integration services and T-SQL, but my main interest is in SQL development and performance tuning. I'm a co-organizer and a speaker at Azure Data Group, Bratislava, Slovakia. If you would like to ask any question after the session, please feel free to reach out to me on my LinkedIn profile, and we can start. Mysteriously Optimized Nested Loops. So why such a title? Several months back, when I've been troubleshooting issues on our production server, internal optimization of nested loops felt like a mystery to me at that point in time. Session will be divided into three main topics: sudden elevation of transaction isolation level, the case of the missing iterator, and unexpected memory grant request. First, the topic will be related to one issue on our production server. Second will be a different one, but it also happened on our production server. So both are real-life examples. So let's talk about issues I encountered on production server during performance tuning. Now, we usually deal with typical performance tuning issues such as missing indexes, parameter sniffing, degradation of performance of store procedures, deadlocks, etc. But this time, it was very strange locking behavior when simple select query blocked many concurrent update sessions on different key values, as if the query was holding locks for more time than usual. Although we run SQL Server with default isolation level, which is read committed. The second issue was excessive memory grant. Well, this is the other strange issue we had, that a simple select query, which caused memory pressure, as it was granted 700 megabytes of memory per execution. And after some investigation, I found out that both the issues were related to the way how nested loops are optimized for better performance. But before we deep dive into the optimization of nested loops joins, I'd like to quickly go through how locking under two transaction isolation levels in SQL Server works. I would like to say a few words about read committed isolation level and repeatable read. Now, let's say we have a table called credit cards, and we have simple select ID from credit cards. Under read committed isolation level, SQL Server needs to place or acquire a shared lock on credit card ID1, read the data, and release the shared lock. Then it goes to credit card ID2, places the shared lock, read the data, and release the shared lock. And the reason why it's happening is because we are using read committed isolation level. We are telling SQL Server that we would like to read committed data. We don't want to read dirty data, for instance, data which are being modified at the time and has not been committed yet, so either rollback or committed. By placing the shared lock on credit card ID2, ID3, etc., SQL Server prevents modification while it's reading this data. So under read committed isolation level, it goes like this until the end of the table or until the end of the index. So SQL Server needs to place the shared lock, read the data, and release the shared lock. Now, under repeatable read, it's something different. SQL Server also needs to place a shared lock, read the data, but it leaves the shared lock until the transaction is rollback or committed. So it goes to another credit card ID 2, places a shared lock, reads the data, leaves the shared lock there until the end of the table. Then when the transaction is committed or rollback, these shared locks are being removed. This way, SQL Server guarantees that while repeatable read is used, all the already read data are not going to change until the transaction is being committed or rollback. Now let's imagine a second situation. There is already a second transaction that is actually modifying credit card ID 5. For SQL Server to be able to modify data, it has to place an exclusive lock, in this example, on credit card ID 5. So it's placing an exclusive X lock, which is incompatible with any other locks. And this way, SQL Server guarantees that while this modification is happening, no other session can modify or read the data. So if there is already a parallel session modifying credit card ID 5 and having this X lock placed on this credit card ID 5, and I'm going to read the data from this credit card table, on the read committed table, read committed isolation level, I place in the shared lock, read the data, releasing the shared lock until the end of the 4 rows. And now, when I would like to read credit card number 5, I'm stuck and I'm in a waiting mode. So I'm waiting to place the shared lock on credit card ID 5, and I cannot because there is already an exclusive lock. And I can place the shared lock only after X-lock exclusive lock has been released. And the repeatable read, it's very same as on the previous slide. So the shared locks are being held on the whole table, and I'm also stuck at the end because there is already an X-lock on credit card ID 5. But the difference between two isolation level, repeatable read and read committed, is that on the read committed, there is only one waiting shared lock on the table, while on a repeatable read, there are 4 already placed shared locks and 1 is in a waiting mode. Now for the demo. Okay, so I have a very simple query. I would like to see some data from sales order header, and I'm joining to sales order detail. I'm also filtering data on this customer ID because I would like to see only data with customer ID higher than 30110. And I'm also ordering by sales order ID. I'm going to run this query under read committed isolation level. So when I run this query, what I've got is 1,423 rows. If I'm going to check if there are any rows still on this table, I'm going to use my snippet, just a second. And I'm going to use session ID 53. Yeah, no logs because we are running in a read committed mode. Now, what I would like to do now is I'm going to open another session. And I'm going to update sales order detail table. So it's this one. And I'm going to update sales order detail ID 111271. So if I scroll down, I'm going to update the last row in a result set. So what I'm going to do, I'm going to update it in an open transaction. So I'm not going to commit it. And I'm going to run my read committed isolation level query. So if I was right, before in the previous slide, it would be stuck at the end of the query. So let's try it. And yes, it's executing query, so it's being stuck on this exclusive lock on the last row of my result set. And now what I'm going to do, I'm going to use another session that I'm going to run in parallel. And this time I'm going to update sales order header. So I'm using my filter condition, and actually I'm going to update the sales order ID 43865. Now, because all my query, because my query already written data, I suppose shared logs have been released and it should go through. But as you can see, it's stuck. And I don't know why, because the query is waiting on the last row here, but I cannot update my first row either. So it seems like there is another session, or there is another lock being held on the beginning of my query. So what I'm going to do, I'm going to check if there are really any locks being held. I'm going to open another session, and this is session ID 53. And I'm going to check the logs being held. And as you can see, there are 64 rows being held on this sales order header table, which is not really what I was expecting, because we are running on the read committed isolation level. And I can see there is no open transaction. I'm just using a simple select query, and I'm still holding 64 rows, or 64 shared logs on 64 rows. So it's very, very strange when I started troubleshooting this on a production server. What I would like to see now is I'm going to roll back my first session, my first update. And yes, it returned all the rows. So I'm going to add the execution plan, because I would like to see what's happening there. I'm going to add actual execution plan. So it's estimated execution plan with runtime statistics, and I'm going to check that execution plan. I'm going to zoom it a bit. And what I have here is very simple select query. So I have one seek operator from non-clustered index. I have key lookup into clustering index using nested loop key lookup. And I have a sort operator for sorting 64 rows coming from index seek operator. And there is another cluster seek into the sales order header. But if you see, there is no operator in this execution plan that would actually cause this lock being held on sales order header table. And this was very strange, because I would try to find the issue, or find the reason why it's happening. And what I can do is I can open this execution plan in Sentry Plan Explorer just to see it clearer. So this is the plan, this is the same plan. And you can see that we had 64 rows read from this index seek. It's been processed by nested loops, sorted, and then I wanted to join them to cluster in index seek. But I still don't understand why these 64 rows are being locked, because I'm still running read committed isolation level. So what I can do now, I can add new. So I was just hovering over these operators, and I'm going to zoom it a bit. Each operator has assigned some node ID value. This one is node ID 0. If I hover over this one, This is, this is node ID 2. If I hover over this one, it's node ID 8. So I'm going to add some additional columns here, and namely node IDs, and I'm going to place them here. So what I can see now is that each operator has its own node ID. But I can see that nested loops operator has node ID 0, sort has node ID 2, so I'm missing node ID 1, which is strange. Then I have node ID 3, and I'm missing node ID 4 again, and I have index seek node ID 5. And I'm missing node ID 6, and then I have node ID 8. So this was very strange. What I also added was two flags. So with ordered and with unordered prefetch. And this is the property of nested loops operator. And I can see that for the first nested loops, with ordered prefetch is set to true. And for the second nested loop, with unordered prefetch is set to true. But it still doesn't say anything about missing operators. So what I'm going to do, I'm gonna go back to my execution plan and my SMS Studio, and I'm going to run this query again, but with additional trace flags. And these trace flags could help me to see how the post optimization has been rewritten. And now I can see that there are operators that I've already spoke about. So this one, nested loop 0, and this is node ID 1. It doesn't say what it is, but it's there. Now I have sort operator, I have another nested loop, and now I have missing node ID 4 operator. Still doesn't say what it is, and I have missing ID 6, node ID 6 operator, but it's a compute scalar. So at least I can see that, yes, there are some missing operators that are hidden from the execution plan. Now, I will go back to my presentation, and I have this execution plan. This is the same execution plan as you've seen in a Sentry Explorer, and I'm trying to add these node IDs here. So I'm missing these node IDs. Now, node ID 6 represents a compute scalar. The sales order header table contains some computed columns, so it's possible that this node was included during the plan's compilation, but as we did not use that column in our select query, this node might be removed during the post-optimization phase. But nodes ID 1 and ID 4 are the missing elements we were seeking for. And if I recall correctly, Paul White referred to these missing nodes as delayed prefetch operator. And I will explain how this prefetching operator operates in the next 2 slides. Now, this is a simple nested loops join operator and how it works. This is just a simplified explanation of a nested loops join utilizing a key lookup in the clustered index. The nested loops operator requests the first row from the sales order header table from the non-clustered index, and this seek operator returns customer ID 30110. So customer ID 110 is retrieved from the outer part of the nested loops, and nested loop triggers the inner part of the operation, which is a clustered key or clustered index key lookup. And since there is only one corresponding row returned from the inner input of the nested loops, once processed by the join, it is returned to the caller. And the reason why there is a nested loops between these two indexes is because index sales order header customer ID is a non-clustered index. It has only filter condition column customer ID, But because I'm using, in my select query, I'm using more columns from the cells or the header table, the seek operator gets the customer ID 30110, but we need additional columns to be displayed. And it is done by using nested loop and key lookup into the clustering index key, because clustered index key contains all the columns in the table. So this is how a simplified version of nested loops join key lookup works. Now, nested loops join with prefetch. Here we have a similar scenario. The first row is retrieved from the outer part or outer input of the nested loops join, returning customer ID 30110 as previously. But this time, however, the optimization known as prefetch is employed. So while customer ID 110 is being processed by the nested loops operator, SQL Server concurrently initiate asynchronous operations, I/O operations, to fetch pages from the disk into the buffer pool and to fetch pages that meet the select queries criteria. So we have now 4 customer IDs already prefetched from disk into the buffer pool. And the reason for this optimization is to preload data pages into the buffer pool so that SQL Server doesn't need to retrieve data from the disk subsystem later. We know that reading data from the disk, from the memory, is much faster than reading it from disk. And this way, the data, when customer ID 30110 is processed, all the other data is already prefetched in the memory. And SQL Server can actually handle the already prefetched data in 2 ways. If ordering customer ID is necessary, SQL Server processes the data sequentially. So customer ID 11 goes first, then 12, then 13, then 14. And it's being processed in this order by nested loops. If the ordering is required, then this with ordered prefetch we've seen in the Sentry execution plan is set to true in the nested loops properties window. If ordering is not required, SQL Server processes the customer IDs in the order they arrive in the buffer pool, and with unordered prefetch, flag is set to true. However, since the query is executed on the read committed isolation level, SQL Server is constrained to read only the committed data. I've already explained this when we were looking at the slide where shared logs are placed on credit cards IDs on the read committed data. But because SQL Server needs to read only committed data, shared log must be applied to the rows while they've been prefetched and placed into the memory. And this time, this is how SQL Server ensures that that key lookup will read only or process only committed data. The downside of this is that shared logs are held until the query is completed to prevent any modification to the rows. And this way, SQL Server safeguards the integrity of the data. And this is exactly why I can see 64 rows being logged by shared logs in my SNS management studio. So now, when SQL Server has all the data, all the customer ID asynchronously prefetched, it can process the customer ID first and then the next customers as well. But because it can cause an issue with login, we can disable nested loops prefetching. So I'm going back to my management studio and I'm going to run this query. So this is the same query, but I'm using the undocumented. I'm using the documented trace flag 8744, which actually disables prefetching for nested loops. So I'm going to do the same. I'm going to update and keep xlog on the last row of the result set of this query. And if I go down, I can see that, yes, it's still running. It's still stuck on the last row of the result set. But if I go to another session and I would like to update the first sales order ID, this time it should go through. And yes, it's been updated. So I can see there are no rows, or there are no shared logs held on this non-clustered index. And also I can prove it by looking at the logs held by this query. So it's query 55, and I'm going to check what's happening there. So yes, I can see that I have one shared log in awaiting mode on a clustering index, and that index is actually, or the key is actually this one, 11271. So this way I can prove that prefetching has been disabled for this query, and no logs have been held on this non-clustered index. So I'm going to close this query. I'm going to roll back now this one. Okay, so back to, what is it, open transaction. So I'm going to close my demo, and I'm going back to my slides. So pros and cons of prefetching. Now, when prefetching is used in nested loops operators, we can get better performance, because when we are reading data from disk, a nested loop has to wait until the page is read from the disk and placed into the buffer pool, into the memory. It can take some time. But while this prefetching is happening, because in the background, these data can already be in a memory, and we can have a better performance. So there is no need to wait for pages to be read from the disk when when nested loops processes other rows. The issue we can have with prefetching is logs are held until the query is finished when prefetch is used in cluster key lookup. So when prefetch is used when we are joining two non-clustered indexes, or we are joining two indexes in different tables, prefetching doesn't lock the pages or doesn't lock the rows. But when there is a prefetch used in key lookup, so we have to find the data, find the other columns from non-clustered index, and we are doing key lookup into the clustering index, then prefetch uses shared logs, and these shared logs are held until the end of the query. The difference between repeatable read and keeping shared logs being held on this while prefetching is used is that repeatable read releases shared logs only when the transaction isolation level or the SQL transaction is committed or rollback. On the other hand, prefetching doesn't care about transaction. It's still being used until the end of the query. So even if I have an open transaction, when the query using prefetching is finished, then the logs are released. So that was the prefetching. And possible solution, if you have issues with locking or strange locking behavior like we had on our production server, you can still use query trace on 8744 in your store procedures, in your queries, as a last row, as a last option. And you can disable prefetching. But of course, when using trace flags, you have to still test. If it doesn't cause more issues, then it helps. So so far we have progressed through an in-depth look at transaction isolation level, elevation, and studied the effects of ordered or unordered prefetch properties of nested loop. Now we are approaching the final topic of my presentation, and this is optimized nested loops. I recently analyzed this real-time execution plan. This is from a production server, and I have anonymized this plan for presentation. We encountered an issue at work where a particular query was using an excessive memory grant. This query was being executed by parallel sessions simultaneously, leading to significant memory pressure due to the large allocation of memory. Upon investigating, the query primarily consisted of index seeks or scans, as you can see, and nested loops join. Surprisingly, this query or this execution plan lacked any operators typically associated with memory allocation, such as sort operator or hash match. But yet the memory grant for this query was unexpectedly high, 700 megabytes. So this is a screenshot of the estimated execution plan, which is anonymized, meaning that actual names of the tables, schemas, and indexes have been changed in order I could present the plan to the audience. I highlighted detail in the plan with yellow, and it's a serial desired memory allocation of 700 megabytes. So what's the serial desired memory? It's the amount of memory the query optimizer estimates is needed to execute the query as a single-threaded plan. To illustrate the impact, imagine if there were 3 concurrent sessions running this query. We would see a cumulative allocation of 2 gigabytes of RAM, each having allocated memory of 700 megabytes. So this is significantly high, even for a server equipped with 64 gigabyte of RAM. Now, it would cause a memory pressure, and it was causing a memory pressure on our production server. And also memory pressure in SQL Server has impact on performance degradation. We would see increased I/O operation as buffer pool, which is in memory, might shrink, and SQL Server would not be able to hold pages in the buffer pool. And for instance, page life expectancy counter would drop. Page life expectancy is an indicator of how many seconds can these 8 kilobyte pages stay in the buffer pool before being removed from memory. Also, other memory sensitive operations such as sorting or hash match may not perform optimally. And also we would see more recompilation of the execution plan because of the memory pressure. To demonstrate the origin of this memory grant, I've prepared a similar query for the demo. So I will go to my management studio. Just a second. Yeah. So I have a simple table, large key table, and it has a ID as an identity, and I've got a new key, varchar64, which is populated by a new ID, and I've got some other columns. I created a clustered, non-clustered index on this new key column. Now I prepared a procedure, large memory, which has input parameter varchar64, and I'm using this varchar in a filter condition. I'm also using this option query trace 8744. It's the same as I've shown before, because I would like to disable prefetching. So I'm going to concentrate on memory allocation. And I'm using maxstop because I would like to see a single-threaded, not parallel, but single-threaded execution plan. So I'm going to create this store procedure, and I'm going to run it with actual execution plan. I will wait a second because I think it's 25 seconds to be finished. It's quite a lot of data. It will return more than 200,000 rows. So we will wait a second. Okay, now it's finished. And as you can see, it's nothing really here. It's just index seek into this non-clustered index. We have one nested loop, we have another nested loop, and we have key lookup. No operators such as sort or hash match, which would require memory allocation. So I will hover over this select, and as you can see, there is a memory grant of 33 megabytes. So this is another issue I was dealing with, that there is no stop and go operator. There is no operator that would require memory allocation, but this query still was granted 33 megabytes of memory. And granting this memory means that even if the query itself doesn't use it at all, the memory is still granted and it's still being blocked and allocated until the query finishes. So I'm going to go to my management studio, and this is the exact execution plan as you've seen. So we have two nested loops, one key lookup, one index seek. So let's explain what is happening. On the right side of the plan, there is an index seek operation. Although it's labeled as index seek, SQL Server is actually performing range scan internally. This is because there is a filter condition in my store procedure where new key like something. And it translates into a dynamic seek range. So there is a constant scalar and compute scalar, and these two operators translates my filter condition into a dynamic seek range condition. And what it means. So SQL Server calculates the start and end points of the range seek. And this picture here is the representation of balanced tree, either non-clustered or clustered index. This is how the index architecture looks like. So we have a root page at the top of this pyramid, and we have an intermediate level, which is a blue one, and on the bottom, gray one, we have leaf level. These are actually the pages that contain all the information stored in the clustered or unclustered index. So SQL Server begins the scan on the root level. It navigates to intermediate level, and it locates the first range condition, so the start of the range condition. And then it scans the leaf pages from left to the right. The scan finishes when the last row meeting the filter criteria is reached. Since non-clustered index rows are sorted by the leading column, so this is the output of the non-clustered index. So the output of this range scan is naturally ordered by the new key column. So we can see actually that the result set of this table or this scan is ordered by new key column, as illustrated in a picture. It's also important to note that non-clustered indexes include the clustered index. So this is the ordering of the new key. And what I would like to say is that all the non-clustered indexes include the clustered index key within the structure. It's ID 420029993. So it's a clustering key. And this inclusion is necessary for key lookups into the cluster index, which is required when columns not present in a non-clustered index, like the CDate I'm returning in my store procedure, CDate column in this instance, need to be returned. SQL Server utilizes the cluster index key stored at the leaf level of the non-clustered index to join rows from both indexes. So SQL Server can, using this clustering index, do a simple key lookup into clustering index. During the optimization phase, the query optimizer might sort the outer input of the nested loop. So it can actually sort these IDs. So the outer input will not be sorted by new key, but it could be sorted by the IDs, which is a clustering key. So in order, this could be enabled when SQL Server sorts the output, the outer input of these nested loops. It can help SQL Server to perform sequential I/O reads from a clustering index. This way, leveraging the likelihood that pages with ever-increasing IDs will be physically close, and this allows the sequential access of the clustering index. So to achieve this, an explicit sort operator may be introduced to achieve this ordering. So sort can be placed in between these two nested loops. However, this operator is fully blocking, meaning it must process all rows before sorting. If the memory grant for the sort operator is underestimated, causing not all rows to fit in memory, a spill to disk to 10 dB can occur, which is significantly slow. An alternative is that, so we do not like to be sorted explicitly. An alternative is the batch sort operator, which can optimize sequential IOs for the inner query of a nested loop. So we are introducing a batch sort operator. Unlike the explicit sort, the batch sort operator is semi-blocking and does not appear in the execution plan. We couldn't see it either in SSMS Studio or SentryPlan Explorer. Its presence is only derived from a memory grant for the nested loops. We've seen this hovering over select operator in the plan, and also by an optimized property set to true in a nested loops property. Batch sort attempts to sort as many rows as possible within the allocated memory, preparing them for processing by the join without resorting to disk spills for the unsorted rows. So if I would like to order 200,000 rows using explicit sort operator, I have to sort it the whole, and I could have a spill to 10 dB. When I'm using batch sort, it does the best effort to order the data coming to this batch sort. So if allocated memory, in this case 33 megabytes, is not enough for sorting all 260,000 rows, batch sort operator will sort, let's say, 50,000 rows and leave it for nested loops to be processed, and then sorts another 50,000 rows. So it never spills to disk, but it still tries to do the best effort to sort this outer input by IDs. So why does the query optimizer choose batch sort over nested loops with an explicit sort of full cluster index scan? Well, the decision is based on the table cardinality and cost estimates. These estimates can be inaccurate. Full scan or explicit sort might be better in such scenarios, but optimize nested loops with implicit batch sort can still offer a satisfactory solution, balancing the efficiency of nested loops and sequential IOs. So what are pros and cons of batch sort operator? Now, pros: this can improve query performance using sequential IO reads in clustering index. If planned with explicit sort, would be better, but optimizer choose not to use it. Cons: not that effective with SSD disk subsystem. Query optimizer is not disk subsystem aware, so it doesn't know if we are using spinning disk or SSDs, but it assumes that we are still using spinning disk. So that's the reason that this might be not that effective with SSDs, and can cause blocking or even lock escalation. It can cause the same blocking as we've seen during prefetch slides, and both optimization techniques, prefetching or optimized nested loops can even do log escalation. So now I would like to elaborate a bit about memory pressure and log escalation, because when optimized nested loops can cause excessive memory grant, for instance, when parameter sniffing issues are used, this can lead to memory pressure and log escalation. As I already said, SQL Server uses logs to ensure data integrity. It places different logs on different objects, but acquiring a log is not the cheap action. Each log is about from, I think, 96 to 130 bytes, if I remember correctly. So let's imagine we are reading thousands of rows, and SQL Server decides to use thousands of row logs. There's already a threshold of how many logs can SQL Server place on one object per session, and that's about 5,000. If the threshold is exceeded, SQL Server escalates row logs to object level. So it removes all the row logs, all the 5,000 row logs, and places the shared log on the object level, which can be a partition or the whole table. So it would mean that it uses only one log on table, shared log, for instance. That's cheap from storage point, but the downside of this is that the whole table is locked and no other session can modify any rows. Now, if we add a memory pressure that these optimized nested loops can cause, also log manager can be under pressure, and this can lower the threshold from 5,000 logs to less, for instance, 3,000, and we will get escalation at 3,000 threshold. So we are in a loop. And why it can cause excessive memory grant when parameter sniffing issues. So let's say my query was granted 700 megabytes to return 4 million rows. It's a query inside the stored procedure, and the compilation of the plan, and the plan is compiled and is reused for the next execution of the stored procedure. Now, let's say I'm using input parameters for the stored procedure that will return only 100 rows. But because these two executions share the same execution plan, the 700 megabytes of allocated memory is reused. Also, although we return only 100 rows. So this is the issue when parameter sniffing is implied. What can we do to avoid this? There are two possibilities. Use trace flag 2340. I wouldn't recommend it because this is an instant level trace flag, and it disables optimization of nested loops for each database. But you can still use hint, disable optimized nested loops inside your query, and this will disable optimization and memory grant for optimized nested loops only on query level. So if I go back to my management studio, I'm going to create a new query, a new stored procedure, or the same stored procedure, but with this option query trace on. I'm going to run it. What I have here. This probably. Okay, and if I go back and I run the same stored procedure, it will return the same amount rows, but as you can see, there is no memory granted. So I've disabled optimization or optimized nested loops and memory grant for nested loops just for this query. So I go back to my presentation. So to sum up, as we approach the end of my presentation, I'd like to sum up the core concepts. I've detailed an internal optimization techniques nested loops joins, specifically prefetching and batch sorting, how it's being implemented, what problem it solves, what issues it can create, and how to solve it. The SQL Server Optimizer is generally quite good at selecting a good enough plan for executing queries. In terms of nested loops optimization, it can significantly enhance I/O performance, and usually optimized nested loops operate without any hitches. However, SQL Server operates across a diverse array of environments, some of which are highly active or handle numerous concurrent sessions. And it is under such condition that these issues may arise. It's my hope that this presentation has enriched your understanding of the internal optimization techniques of SQL Server, and that this knowledge will assist you in identifying and resolving such issues at the query level. Should you have any questions following this session, if you require further information, please feel free to reach out to me through my LinkedIn profile, provided also at the end of the presentation. And if you would like to read more about the optimization of nested loops, I would recommend these 4 links. Craig Friedman wrote the first blog about it in 2008, so it's 16 years old. So it's been there. I just never read it, and until recently found out this issue on my production server. If you want to know some internals of how prefetching works, please visit Paul White's blog. Fabiano Amorim wrote a nice blog about performance of these prefetching. And if you would like to know more about internals of how nested loops work or any other operators in execution plan, please visit Hugo Corneli's blog. And thank you very much for attending my session. Hope you enjoyed it. And I would also like to thank the organizer of the conference, which is a perfect starting point for new speakers. And I also would like to thank my mentor, Sasha Lawrence, for guiding me through the session preparation. Thank you.